Welcome back. So first of all, I'd like to thank Prasanna for organizing this workshop, and then all my colleagues who gave excellent talks in the morning session. So this would be touching upon some of those ideas, but the main focus of this talk would be about transfer learning in this hyperparameter optimization, right? And as Prasanna said, I'm going to talk about a demonstration on this for like an audit training problem. So let me see. Yeah. All right. So first, let's talk about what is the motivation for doing, say, transfer learning, right? So especially there are two things that comes in mind. So one is this case of mixed categorical continuous spaces that are very difficult to navigate, and another challenge would be to work with this forward models that are black box models, such as neural networks that are only getting deeper and wider by the day. Right? If you see the plot here, you can see from 2018 to 2021, the number of parameters in the model have just grown exponentially, right? From around 94 million to now we are looking at trillions. So if we want to optimize the hyperparameters on a very large model, we might want to reuse some of the information gained from the previous optimization runs or related data sets, so that we don't have to do as many expensive evaluations of the model if possible. So this has been touched on earlier in Prasanna's talk, but we are interested in the search space that consists of integer parameters that has like an ordering. You can think about the number of nodes in a layer as an example, or we can have continuous parameters that can take real values such as win rate, or categorical parameters that don't have an ordering, such as a choice of an optimizer. So this is a non-convex mixed integer nonlinear programming problem, which we call as MinLP, and this is known to be one of the hardest optimization problems. So given that, an intuition for if we keep in mind the computational intensity of the model evaluation and the challenge in solving the MinLP optimization, the transfer learning intuition is very important in this case. So once we have evaluated a hyperparameter search, we obtain the samples from this configuration space that has been evaluated, right? So the configurations that are around the best objective values represent the subspace, which is highly performant in this parameter space. Typically, if you think of a prior hypothesis space, as in when you're defining a hyperparameter search, you define intervals in which you want, or bounds in which you want to do the search. But typically, the high performing region lies somewhere in a small region or a neighborhood, right? And when we identify such a neighborhood, like what we want to do is, when we are doing transfer learning for a similar problem, we want to, instead of using this large uninformative space, you can try to constrain that space through this idea of informative prior, so that we decrease the space in which the search can happen, right? So when we do that, in theory, we can see that the model in this new target scenario can converge faster to the optimal solution for the particular problem. So given that intuition, I'd like to talk about this generative model approach. So basically, when we get when we get a set of configurations that we have evaluated from the source data set, what we want to have is like a parametric model that can represent the joint density of these high-performing subspace, right? And a natural or frequently used approach, or a popular approach for building such models is a generative model, and especially the variation autoencoder has been widely used recently for developing generative models of large data, like such as images, right? But in this space, as we have seen, we have a mixed categorical and continuous variables, right? So a typical BAE or typical generative models don't work so well. So in this case, we adopt a tabular version of the variation autoencoder, where the main idea is that the decoder over here, which outputs additional quantities that define the probability under the multimodality of the space, and also give separate parameters for your continuous and discrete variables. So all said and done, once you train this model, you will be able to sample configurations in this mixed categorical and continuous space. So more details of this model can be found in this reference. Right. So, going back to the explanation of Bayesian optimization, right? Typically, Bayesian optimization starts with user-defined prior distributions, like as I say, uniform distribution on each parameter. The main difference in this transfer learning strategy that we are adopting is that we build a joint distribution of these high-performance configurations using this tabular VAE approach, and we use that particular generative model to sample configurations instead of generating them randomly from that uninformative space. Right. So we first train this TVAE generative model, and from which we will be able to generate more samples this way, right? So once we train the model, we have this decoder part of the network where the latency, random sample from the latent space corresponds to a sample from the mixed categorical and continuous distributions. Right? It means we are able to generate more samples that are similar to the high-performing configurations. So these configurations can not only be used for initializing the Bayesian optimization when the search begins on the target search space, but also it can be used to bias the search as we are evaluating more configurations as the search happens. So, this strategy inside a Bayesian optimization can help the exploration and exploitation for this target problem, such that it is biased towards the high performance configurations of the source learn. We call this approach as the variation autoencoder guided asynchronous Bayesian optimization, or the VAE ABO. And so this is an overall description of the algorithm, and I'll run through each of the steps of this approach. So initially, at the first step, we chose the search history, which are the configurations that we have evaluated from the previous searches. And then we chose a quantile value, right? Quantile value defines the part of the configurations which have high objective value, but which lies in this distribution interval of a normal distribution. So, for example, if you pick like a quantile value of 20%, we are going to pick the top 20% of the configurations, right, to build a generative model. And then we define DP as this domain of the previous source problem, and DC as the current search space, right? So you can think about two scenarios, right? The first scenario, maybe I can touch on in the next slide. So once you have that subset of configurations that you have chosen from the source data, then you can build this tabular VAE model as a distribution of a generative model that represents the data that or the configurations that we have previously evaluated. So Yeah. So once we have this tabular VAE model trained, then we look at the what's the target search space, and now we can come across two scenarios, right? The first scenario is in which the source and the target has the same parameter space. So in that case, we can directly start with the generative model that we have trained to bias the initialization and the search. But in the case where we have some additional parameters, like in addition to the common parameters from the source and target, we should have a way to define them in a non-informative way. So the way that we do here is for the real parameters or continuous parameters, we chose that to be a uniform distribution with some bonds, LJ and UJ, which is typically what is done in the non-transfer learning version of the Bayesian optimization. And then for the categorical parameters, we chose a multivariate distribution with equal probabilities for all the categories, right? So now the asynchronous Bayesian optimization in DeepHyper starts by sampling parameter configurations based on this informative, what we say, distribution, a generative model that we have trained on the previous configurations. And once we have this notion of the generative model, then the other steps that follow in the asynchronous Bayesian optimization are same as the non-transfer learning version. Right. So, like that said, we want I'll show a demonstration on so basically how the transfer learning works. On this HPC data service audit problem, which we recently looked at, right? So in this talk, I'm not going to go into a lot of details on this audit tuning work, as in the problem, but in the interest of time. But I would like to mention that there are a total of 20 parameters that define the different stages of these audit tuning framework, and also it's important to note that the computational intensity of this problem can be made arbitrarily large depending upon how much data is being transferred and how much compute resources are used for doing the transfer. And the objective in our case is to find the configuration that reduces the runtime of these services, right? So, and the first scenario that we are going to look at is this case where we are expanding the search space systematically, right? So in the first configuration, we have 11 parameters, which define this process of loading data into the workflow. And there is the second part of the configuration space consists of 16 parameters, where the 11 are common between them, and it has 5 additional parameters. And finally, this is the full 20 parameter space, where it involves all the bells and whistles needed for this audit tuning problem, right? So to put it in the context of neural networks, right? So we can think about this as a case where we train a set of hyperparameters of neural networks, and at the later stage we want to add or search over some additional parameters, right? So we don't want to do the search right from scratch, and doing this kind of a transfer learning will help us to converge on good configurations for the additional parameters without a lot of evaluations. Right. So here I'm showing the evolution of the best configuration found by DeepHyper with our transfer learning in this expanding search space scenario. Right? So as you can clearly see here, when we are using transfer learning, the search what we say converges to a good performing configuration almost instantly, right? But when you see without a transfer learning, it takes a lot of time. It's much more variable, and it takes a lot of time to converge to the same configuration. Like we go from 11 to 16 to 20, and you can see like in this case it's almost instantaneous. And the configurations also found by transfer learning and without transfer learning are very close together, which means we are able to get the same accuracy in the results with fewer number of evaluation and less search time. Yeah, so in the second scenario, this is the case where the parameter space is the same. So the number of parameters that we are searching over are same, but the computational intensity of the problem is changing, as in the time taken to evaluate the models increases, right? Because we are using more resources in a way. So even in this case, you can see that as we keep going into these more computationally intensive models, when we are doing transfer learning, it is able to find this high performance configurations very quickly. And while without transfer learning, you can see it is taking much longer to converge. I'll give some, okay, yeah. So here, this slide actually puts it in perspective, right? So here I'm showing the best configuration that is being found with and without transfer learning, and the way how much speed up that we get when we use transfer learning, right? So here you can see here that the configurations that are found by transfer learning are better or at least as good as the ones that are being found without transfer learning, doing the full run from initialization. And this is very interesting. You see that the speed ups that you get are on the order of 40 times, right? So we get 40 times speed up compared to a random search, where without transfer learning and with the asynchronous Bayesian optimization, we get a speed up of around 2.5 to 10 times. So that's like at the least, it's a 4 times speed up compared to without using transfer learning. And we also do a comparison with other approaches in the literature that does Bayesian optimization and support some form of transfer learning. And clearly, we can see in this case, that the configurations that are like obtained with DeepHyper, in this case with 10 workers, is shown to be to find a better configuration compared to the other approaches. This gives us increased confidence that we are able to find better configurations faster with much fewer evaluations, and compare very well with the other transfer learning approaches out there in the literature. So, like at this point, we will be discussing a toy problem on transfer learning of this hyperparameter space in the hands-on exercise. But I'm glad to take any questions that you might have now on the transfer learning approach as such. Okay. So I can stop share. Yeah. So does anyone have any questions? I'll just leave this here.
If I understand this correctly, so you are using transfer learning to speed up the hyperparameter optimization, right? So based on a similar model or similar model, or, yeah.
So based on it can be like a previously run hyperparameter search that you have done on models that are run on similar data or have a similar space. In a sense, they are related to the problem that you want to do.
Okay, so this is basically kind of an approach to the main question that everybody has on hyperparameter optimization, is like, how do I start, right? So nobody, if you don't know anything about how to start, everybody wants a base model or something like that. So this will be a great solution for that, you'll say?
I would like to comment that we have to be very careful in terms of picking the related problems, yeah. Right? Yeah, so to initialize in a way, warm start your optimization, hyperparameter optimization. Yeah, we have till now experimented with search spaces that are similar between source and target, but it would be interesting to see how much speed up or otherwise we would see when we're looking at different search spaces like different problems. But yeah, this can give a way in which you can like start your search on similar problems. For neural networks, you can imagine like if you have a model trained on a certain image data set, and you want to train your model on a slightly different image data, but you think that the features in those data sets are similar, then this could be one way you can adopt or transfer learn your search space.
So is it like reducing the search space, or in a way it is reducing the search space, but like the mechanism here is that we're trying to transfer some learned parameters from previously explored spaces, right?
So we are not necessarily reducing the search space, but we are going to reduce. So the promise is that we will reduce the number of evaluations that you need to converge to a good configuration.
Yeah.
Yeah, so it's not, in some sense, it's not a hard reduction, right? So we still have positive probability, so to speak, but in the using this bias samples, we say we will be like, okay, so we already identified some promising regions of the search space. Let's say the learning rate is between 10 to the power of -2 to 10 to the power of -3. The original range is 10 to the power of -5 to 1, right? So on this task, okay, we already we ran a hyperparameter search and we already identified, my range is between 10 to the power of -2 to -3, right? Yeah. And now you don't want to again go back and start the search from scratch, right? So that is this is more like, okay, I want to concentrate more on this 10 to the power of -2 to -3 range, right? Now think about, for one parameter we can do this in a very straightforward way. But if you have like 20 parameters, how are you going to do that, right? So, using this mechanism, you sort of, bias your search towards already identified promising regions. So that's the sort of, in a nutshell, so to speak.
Yeah.
And like we can also capture the correlations between these multiple parameters through the generative model. When you're biasing the search.
Yeah.
Yeah, but it's just like on a different context, but this does not kind of guarantee that it will hit the global minima, right? We can be stuck in a saddle point also, or do we have to again spread our search just to make sure, okay, the one?
Yeah, so that is very true, right? For mixed integer nonlinear program, it's impossible to come up with global global optimality unless you make simplifying assumptions. At that point, it's not useful in practice, right? So it's a mixed integer. It's not only mixed integer. It's a mixed integer. It's already a hard problem, and it's a mixed integer nonlinear program with no derivatives. No, it's a complete black box, right? So it's one of the hardest mathematical optimization problem that you could ever think of. So global convergence or global optima, like neural networks, even in neural networks, you have all real parameters. Even then, there the problem is a lot of parameters, like thousands or millions of parameters. So that's why proving convergence is hard. Here you don't have million parameters. You have let's say on the order of 20 to 30 hyperparameters, mixed integer. But you can try to find some high performing configurations in a much faster way, as opposed to trying to explore this in a much more, starting from scratch. So that's the that's the idea.
Yes, thank you. Yeah,
I mean, we do this, right? So manually we always do this, right? So we run an experiment and say, oh, okay, so these are the good regions, so let me do another search with fine tuning this and this, right? So this is much more systematic way to approach this problem, and we can scale this, right? So it's scaling with respect to the number of hyperparameters, and also we can run this in parallel. So, we can use multiple workers to do this and so on and so forth. That's why in many settings, we can hit the best configuration almost immediately.
Yeah.
Yeah,
Okay, I
that's
showed in
really
the search space contraction image, right, initially. So you're essentially in a good neighborhood, and only few evaluations will take you to the optimal region.
And often in these type of problems, like mixed integer problems that with the respect to hyperparameters, often the global optima is not, in terms of performance, it's not quite far from good local solutions. We in some sense we don't have a theory for it. It's more a practical observation that in many settings, even if you run it longer, the amount of improvement that you get is not drastically different from some high quality local solution.
Yeah, that's actually very cool, very nice, like, because it's reducing our design time also, so it's very useful that way.
Yeah.
Okay.
Yeah, so it's an unrelated problem, but in general, we also saw that in some scenarios, finding good set of hyperparameters transfer well in cases where such continuous learning, like when you have different tasks and such, finding good hyperparameters actually transfers well when the distribution of data is changing as well. So that could also be an interesting problem application for this method.
Am I correct in understanding that this is more general than, so initially also there's a talk on hyperparameter optimization specific to like neural networks like optimizer and so on. So this is like a more general framework for like multiple like hyperparameter selection problems, or like how is this different?
So you were spot on. So the capability, the algorithm itself, it's not particular to neural network. Of course, we started with neural networks, right? So we wanted to do hyperparameter optimization with neural networks, and then that's a nice thing about Argonne. We have diverse set of team asking like, okay, we want to solve diverse set of problems, and then these our data services and IO folks came and said like, oh, we have a problem, hyperparameter tuning problem, but it's not related to neural network. I say, okay, bring it on. And then we did this, and somehow they pushed us towards transfer learning. Said, hey guys, we cannot run this each and every time. We do this incrementally. We start with 10 parameters, and then we add 4 more parameters based on that, because they have some internal parameters which they don't expose in the beginning, right? Like in the neural network code, we expose all the parameters in the beginning, but in the data services case, they don't expose all the parameters. They didn't even thought about like exposing those parameters in the beginning. So like, okay, we start with these 10 parameters and then we tune and said, oh, okay, so we can also expose these 4 parameters. Now we don't want to run the search from scratch, running, starting from 14 parameters. They said like, okay, we already have results for 10 parameters. Now we can use the results to bias those 10 parameters in the search, and then do a more search for like those 4 parameters. And we don't do this. We don't fix the 10 parameters, but we let this search run along with this 10 and 4 parameters, right? So that's how we ended up, and we also saw that there's a lot of use cases for neural networks as well, and there are other black box optimization that one could potentially cast into this framework. So parallel Bayesian optimization for mixed integer. Yes, you are spot on. Like it's much more general than neural networks.
So the hyperparameter optimization strategy is that was describing even in the morning, and here this is completely applicable to any problem, any black box problem.
But also, we have to be a little bit careful here, right? So we don't want to overpromise. So this is all based on beyond neural networks. We are sort of limited in our experience, in the sense that we are looking at these type of problems and we are using them, So far, the results are good, but it's always possible to come up with a counterexample where these things don't work. So we are slowly building some understanding, and also we are looking into ways to sort of develop theories related to that. How can we develop transfer learning theory for mixed integer hyperparameter optimization, and this can be sort of casted into continual learning. And Krishnan, who's presented this morning on uncertainty quantification, so he's doing a lot of fantastic work on continual learning theory. So we are also thinking about how to bring those theory into these aspects and get some sort of guarantees, certificates, and provable convergence and things like that. So it's a long way down, but it's a really a promising direction.